this talk. So, Peter Szilagyi.
Good morning, everybody. So, unlike many of the crypto projects out there, Ethereum isn't really an end-to-end product. It has always been a platform by developers for developers. And as such, our primary task is to make developers happy, so that in their turn, they can make their end users happy. Now, to achieve this, in my opinion, one of our most important roles is to either aid the existing tooling, developer tooling out in the community, or maybe fund or create new ones that the ecosystem is currently lacking. And my talk will be about one such tool that we wrote. But before we dive in, let's see what the actual pain points are. Usually, when the developers approach Ethereum for the first time, they start playing around with Remix, this browser Solidity playground. They get the hang of Solidity. They start prototyping their contract. Now, unfortunately, quite fast, they realize that developing in a web browser is cumbersome. So they switch to more sophisticated tools such as Truffle, which can do automated, repeatable testing, and also aided by proof of authority chains or instant transactions. Now, after developers actually finish writing their code, usually the procedure is that they deploy it on a testnet, either Robston or on an alternative, because that's really nice. It's a real-world environment, many users, etc. Now, the problem is that this perfect testing environment often goes belly up. And the reason is, one of the reasons is that the test networks can be really heavy, either due to spam attacks or to large projects such as Raiden doing intensive tests. These can be unstable from time to time, usually because somebody figures it would be fun to reorganize the chain. And lastly, it can often be unfriendly because you have this awesome project you want to deploy, but you don't have test ether, and that's annoying. And the truth is that if you are a small project, then running testing on the testnet is fine, but if you're a bit larger project, such as Raiden, or maybe have many projects such as Consensus, or perhaps you want to run a hackathon, then the live test network isn't really ideal. So the ideal solution is actually to run your own network. Now, this might seem like a good idea at the beginning, since it's light, stable, you have unlimited funds, you can share with everybody. But when you actually start configuring your private network, horror strikes in. So it's actually quite a nightmare to configure, because it has gazillions of different moving components. And so we've been working for quite long on a tool called Puppet. And the goal, our primary goal with Puppet was actually to run the Rinkeby testnet on it. But we kind of realized that it will be an amazing tool for, at least we hope an amazing tool for other projects too. So we kind of polished it up and gave it out to the community. And for the rest of my talk, I'm going to do something really crazy. I would like to demonstrate what it takes to actually create an entire Ethereum network with bells and whistles live on stage. So first up, if you want to actually start your Ethereum network, obviously you need to configure the Genesis block, the shared initial accounts, the balances, and you have to define what precompiled contracts you have, what fees they have. Now there are different fork rules that you need to take care of. And if this wasn't horrible enough, if you have to do this for the 5 primary clients, that's about 414 configuration values. And that's just a snippet from Parity's really extensive list. So that's not really a pleasant experience. However, if we try Puppet, now Puppet is a command line tool, but kind of a command line wizard to help you. So the first thing, it just greets you with a nice message and asks, what network would you like to manage? We'll just type Devcon. That's a nice network. And then asks, what would you like to do? Well, we don't have network yet, so we cannot show network statistics, but we can configure the Genesis block. So let's just switch that. And what kind of consensus engine? Well, we have proof of authority for Click, but since we want actually a cross-client network, let's stick to ET hash. Nice. Do we want to fund initial accounts? No. And do we want a specific network chains? Well, if you run a public network, maybe it's worthwhile. No, for now, we just do random. And that was about it. We actually managed to configure an entire Genesis state for 5 different clients without doing anything. Now, of course, if you actually want to run your own network, then the Genesis is just step 1. You would need to get some nodes online. But one of the biggest problems that we see with people getting nodes online is that they have absolutely no idea what the nodes are doing. So you really need to monitor the nodes somehow. And we really want to do that via an ETH-stats, or running ETH-stats, which isn't really easy to do, but let's see how Puppet can help. So what would you like to do? Puppet asks us, well, we'd like to deploy a new network component. It gives us a choice. Let's stick to ETH-stats. And which server? Well, let's connect to a server. We have a server called Devcon Network. It's a registered domain name. Connect a new server, Devcon Network. And yay, Wi-Fi works. Awesome. So we managed to connect. That's why you don't do live demos. Devcon Network. Do we trust this? Yes, we trust the remote host. Cool. Now where do we want to deploy ETH? Since we want to deploy possibly multiple websites here, let's deploy it on port 80. And do we want to share the port 80 with others? Yes, sure. Now, when we actually say we want to share port 80, Puppet will deploy a reverse Nginx proxy, automatically configure everything without us having to do anything. And what domain do we want to host this ETH-stats page on? stats.devcon.network. OK, and what's the ETH-stats password? Hello. Hello, it doesn't matter. Yeah, it's fine. Now, in theory, Puppet now runs in the background, starts up entire ETH-stats and everything. And now, not only will it start it up, it also lists us that, yes, we have a server connected, the IP address, and what services it's running. And now, if you load up a web browser and look at the actual domain name, then hopefully, yep, we have an ETH-stats running. And you can see it is actually not an image, it's a live stats page. OK. Now, we can monitor the thing, but we actually have to boot up the network. So let's deploy now a boot node. Yeah, sometimes the console is funky, but it will. Now, again, we have a small scan so that we know what we're up to. And let's deploy a new network component. Yep, we want to deploy a boot node. And where do we want to deploy it? Well, usually you don't want your boot node to go down if somebody's DOSing your website. So let's just switch to a new server. Let's call it boot.devcon.network. And yes, we connect to the new server. That's fine. We can manage multiple servers at the same time. Where do we want to store the data directory? Let's call it Devcon boot node on the server. What UDP port one? We'll just go with the default configurations. They aren't even that interesting. And what do we want to call the boot node on the stats page? Let's call it boot node. That seems about as dumb as it can get. And again, Puppet does its funky magic in the background. And if I think I can even close this. Yep. And if we now check our stats page, then, yep, well, fair enough, we have our boot node registered. Maybe it's not a bit tiny, but we have a boot node running, and it's immediately linked to the stats page. We don't even have to configure everything. Cool. Now, we have a static chain that doesn't do anything. Obviously, we need to mine on the chain to make it progress. So we can, again, ask startup Puppet, ask it to connect to our new little network, and let's see what it takes to deploy our mining node. Now we want to deploy a new network component. Let's deploy a mining node or a sealer. Again, miner kind of takes a kick out of the machine, so let's put it on the miner.devcon network machine. Yep. And where should we store the data? Devcon miner. And where should we store ETH hash DAGs? Devcon ETH hash. Yeah. And the remainder can be, the connectivity strings can be simple, and we want to register it on the ETH hash page, ETH page as the miner. Now what Ether base should, ooh, that was fancy. What address should the miner use? We'll just copy paste this here, and what gas price and gas targets, we'll just stick to the defaults. It's not that important. And again, Puppet is pushing out the mining node to our remote server, and it should finish booting any moment. It does a quick health check. It actually checks whether the ports are reachable. We have a nice dump of everything we configured until now. And if we look at the stats page, fingers crossed, yep, we actually have already 4 blocks mined. And not only that, I'm really hoping that the boot node will connect soon to the mining node. But since time is limited, we'll just check it in the next slide. Yep, they've connected. Cool. So, of course, now you actually have an entire network up and running, but if you tell your friends that, hey, I have this awesome network, they will just go, okay, and how do we use it? And then you kind of start scratching your head. So it would be really nice if, well, first thing first, you could see what the network is doing. So for that, obviously, we need kind of a block explorer, which currently, for example, there is no open source block explorer that supports Go Ethereum as a backend. But however, there is one that supports parity. Now, can we actually deploy a parity node easily? Well, sure, let's try. We want to deploy a new network component. Let's do an explorer. Where do we want to deploy it? Well, we will put everything, all our websites on the same machine. So let's use Devcon network as the machine. Yes, we want to share port 80. And let's do explorer devcon.network. Where should the data be stored? Devcon explorer. And the defaults, let's call it on Explorer on the stats page. And again, it's pushing it out fairly fast, hopefully. I'm just waiting for the node to finish booting. Yeah, I'll just close it. And let's see, does it actually work? Fingers crossed. Yep, we have our block explorer up and running, and we have already 11 blocks mined. And we can check that our miner already has 42 Ether. Ooh, that's a nice number. And of course, if we check the network stats, then again, we already have 3 machines running without actually configuring too much. Okay, now we know what the chain is doing from the inside and from the outside. Can we ask our friends to use it? Well, sure, but it's kind of hard to use it via a simple client, so let's try to give them a web wallet. Now, of course, everybody knows the most sophisticated web wallet currently out there is MyEtherWallet. So let's just deploy MyEtherWallet to our little custom test network. So let's just deploy a new network component. We want to deploy a wallet to our website server. Yes, we want to share port 80 and call it wallet.devcon.network. Where should we store the data? Wallet and just spice up the defaults a bit. And let's call our wallet on the stats page, since that runs also backend node, let's just call it wallet. And again, Puppet is just configuring everything in the background for us, and it is pushing out the data. And if we check our wallet now, this is something that takes usually the most time to boot up. Yeah, boom, we have our wallet. And as you can see, it is actually configured for the Devcon network. It deployed a backend node to connect to. We have the front end, and everything seems to work nicely. Cool. So that one kind of was easy enough to deploy all the components. But if you share this with your friend, then he'll say that, OK, I want Ether, and you will be the one who has to give them Ether all the time, which gets boring really fast. So we really need a faucet that you can just start up, and it just runs there, and everybody can request Ether. And to do that, we have Go Ethereum has a faucet built in, or support for it, based on the Lite client. So let's ask Puppet to deploy that. Yep, we want to deploy a new network component. And let's do faucet. That's our 6th on the list. And we want to deploy it again onto our web server. We deployed everything there. Faucet, Devcon network domain name. Oh, yeah, sorry. Port 80 first, and then faucet. Devcon. Oops, thank you. Ooh, nice. Okay, how many Ether do we want the faucet to release? Well, 1 Ether is fine per 15 minutes. We want 3 tiers. If you wait more, you get more Ether. Do we want reCAPTCHA protection against bots? No, it's a test network here for Devcon. We don't care about robots. Where should we store the data? Devcon faucets sounds about right. And let's just pick a different port for this one. What should the faucet be called on the stats page? Faucet. Of course, if I run a faucet, I do need a private key so that the faucet can actually fund its stuff out of. So we have a private key pasted in here. We have to unlock it for the faucet. Boom, it's unlocked. And do we allow unauthorized requests? Well, since it's a Devcon and we don't care about the lifetime of this whole network so much, yes, we authorize anyone to request funds. And let's deploy it. It managed to deploy. That was nice. And now comes the moment of truth. Can we actually, as you can, again, we have a nice dump of all the configurations. Now, can we actually load up the faucet? Yep. Oh, why is it? Yep, we have a Devcon authenticated faucet. And if we request funds now, into an Ether address, give me 1 Ether. Yep, the faucet accepted our funding request, and if the miner manages to mine us a few blocks, yep, we just mined it, and we have our account funded. And we can also check the stats page that everything that we deployed until now have indeed appeared on the stats page. Now finally, you deployed everything, but you don't even know what your Genesis block is, you don't know how to connect to it, and it's just a mess of different websites on different domains. So you really want to deploy everything on a single host, or at least on a single place that your users could find it. And the only way to do that is to have a nice dashboard. And that is actually the last thing that Puppet can do currently. And let's just try to do that. We're just having a nice, deploy a new network component. And the final piece of the puzzle is a dashboard. Let's deploy it to our website. And let's use the root domain, devcon.network, for it. And then it will ask, which services do I want to list? Yep, I want to list the stats page. I want to list the block explorer. I want to list the web wallet. And I want to list the faucet. And do we want the eStats secret to be public? Yes, let's make it public. And Puppet again crunches everything, makes the configuration files, deploys a web server for us, and if everything worked correctly, I should be able to load up a nice dashboard. Yep, and we have, at first page, we have the eStats. On the left-hand side, we have a nice sidebar menu where we can switch between the eStats. We have the block explorer that we just configured. We have our web wallet that we can play around with. We have the faucet to request all the funds that people are requesting funds. Amazing. And and beside all of these services that we configured, we also have detailed guide on how to connect Go Ethereum in archive node, full node, live client, or embedded for embedded machines. We have details on how to connect Mist and Ethereum wallet. We have details on how to connect Android and iOS devices. And finally, if you really don't prefer Go Ethereum as your client of choice, then we also have details on how to connect C++ Ethereum, Ethereum Harmony, Parity, and PyEth app. And ladies and gentlemen, that was the Puppet Network Manager. Thank you very much.
Good morning. Let me see, where are we? Next up, we have Marcus Liggy with his presentation and introduction to Walleth, the Ethereum Android wallet.
No, that's not my screen. And that's the wrong presentation. But my screen is connected. Yes, that's the right one. Yes. Greetings, each and everyone. Great to be here. Like bright sun, bright minds. What a great combination. In this talk, I want to present to you Wallet, the Android Ethereum wallet. And we will focus on three things: the why it is, what it is, and where do you find it, basically. As many of you, I'm really fascinated by the idea of a world computer. Like, I love this world, I love computers, and the combination is like really awesome. And I also think that we can protect this Earth by managing the resources way better by using Ethereum. As we are at an Ethereum conference, I don't have to preach to the converted and tell you why Ethereum is awesome. I just want to add one thing. What I really like is the upgrade path to proof of stake, so that we don't have to burn so much energy to have the consensus, that we can have it without hurting the environment so much. I really love Bitcoin for the spark it brought to the world, but I really don't like it for how much energy it consumes. And I want to quote the great Greg McMullen from a conference this year, because it's often forgotten. Blockchain is about people. The technological parts are really exciting. The tools are powerful. The engineering challenges are huge. But first and foremost, everything we build is about people. One really nice way to bring Ethereum to people is Android. This is a screenshot from this year's Google I/O. Like, there are 2 billion monthly active devices, so it's a really nice vehicle to bring Ethereum to these people. And it's also good for emerging countries, because often you see people don't have PCs anymore. They use phones. I'm doing mobile development since a long time. I have a really dark history of Java for micro editions. And Android was basically my savior and saved a lot of problems, so I'm really a huge Android fanboy. And one of my apps is Passbook for Android. And there it's a nice connection to Ethereum, because if you treat tickets not as passwords as it is currently, but as tokens, you get really, really nice properties. I gave a talk about that at the Ethereum office in Berlin. If you want to look that up, please do. But when implementing it, I found out there are some building blocks missing to build what I wanted to build. So that's why Wallet, I needed to build that first to basically get where I want to go. And why? One big reason why I didn't want to use wallets that are out there is they didn't fulfill my constraints. The first and most important constraint I had to a wallet is that the keys have to be in the hands of the user and not on some server, because I think that doesn't really fulfill the purpose. And I could not even sleep having all these keys from other users, and I really like to sleep. So, and you think that's quite obvious that the keys should be at the users, but then you see the most used wallet currently is something like that. And you obviously see the keys are not at the users, and then you have basically a centralization again, and that's really not what we want. And yeah. And I also think it has to be Libre software and not closed source software, because even if the keys are in the hands of the users, but you have closed source software, the keys are not really in the hands of the users. And it's not only small parts, like some apps have only small parts open, but it has to be the full app has open. And I want to go even further. Not only the app has to be open source, but also the platform has to be open, because it's basically the weakest link in the chain. Like on iOS, even if the app is open, Apple could steal all your keys. And in Android, there are no movements to really open up everything. Like, for example, Purism, a phone where there's no more closed blob, or nice movements like the Fairphone. So let's dive in the app, but I have a drink a bit. That's how you're greeted. Because I think the user experience is really important and often missing in tools today. So basically, I guide the users in that he can get first his funds. And after pressing there, you see an ERC67 QR code, so you can transfer funds to that. For example, from the nice Go Ethereum faucet. And then after you transferred something there, you see the incoming transaction there. And you might have wondered, a lot of other wallets ask you for a password first. But I also think that's a stupid thing because it really hurts the user interface, because often you just want to try out things at the beginning. You don't have accounts that have huge value. You just want to try out things. But then basically things force you to enter a password. But I think the user story should be different. The user story should be that you basically can try out things, and when the account gets real value, then you secure it. And then I even think you shouldn't secure it with a password, but you should use a real hardware wallet, because that's real security. Because a password, we can discuss it in a break, it doesn't really add much, especially on Android, where you have a sandbox. You really need that on a PC, where every app can see the data of another app. But on Android, all the apps are sandboxed, so a password doesn't really help and often gives a false sense of security. Another thing you see in the app there is the scan button. It's the floating action button from Aetherium Android design, and it brings you to different places. You can scan ERC67 from, for example, another app. You can import a JSON UTC key or a raw key or a plain address. Unfortunately, a lot of people don't use ERC67, so raw addresses are like really a pain, but they're out there. And you can scan signed and unsigned transaction RLP that helps for offline transaction modes. I will talk about it a bit later. A bit more filled, it looks like that. Basically, on the left, it's the incoming row under the incoming button, and on the right is the outgoing row, because I love for it to be a balance. I think value should not pile up, value should flow in and flow out. I'm breaking a bit there with the user interfaces of other wallets, but I think that's okay. I try to keep a concise visual language. There you see different transaction states. You saw before always at the icon there. There's unsigned transactions. When you don't have a key, you can have watch-only accounts. You have signed and confirmed, but for example, not transacted because you're offline. Then you can even delete them, but only locally. They might be already sent. And then full black is signed and confirmed on the blockchain. You cannot delete them for sure. Let's look in the navigation drawer. There you can edit your account. Very important. Always your keys, your account, not your keys, not your account. Import and export keys. Some settings, offline transactions, very important. And debug at the moment, it's alpha, so debug is very important. So you can see the Go Ethereum things. You saw this left icon before. I don't really use and like the blocky icons, so I really want to use Peter Szilagy's Flame IDs. But they're same thing with the building blocks, because to calculate these Flame IDs takes 7 seconds on the 1070 GPU. So we need TrueBit and stuff first to get that stuff secure, because I cannot calculate that on the phone. Yeah, here you can edit your account basically. With the camera, add a watch-only account. With the key, generate a key. And Trezor, very important. I think that's the first wallet for Ethereum Trezor support. I think hardware wallets are the key for security and are also an option to be a metaphor for users, because they know if they have a hardware wallet, it's really their key. Because only if the key is on your device, you're not really sure if you're in control. But a hardware wallet can be a nice metaphor, like your X metaphor. I try to use common symbols. These are from material icon design, to always be concise all over the app, that you can educate users that they have a nice experience. So scan the code, offline transactions, Trezor, share, private key, and copy some content. And that's all over the place. They're always the same. That's how it's looking when you add a Trezor device. Then you have to enter your PIN. I don't know if a lot of people of you use Trezor so far. There you don't see the numbers because the numbers show up on the Trezor so that your device can never access it. You can, that's optional, add a password. And there you also have plausible deniability. Really nice feature from Trezor. Then you can select an account from the Trezor with the derivation path. I have to speed up a little bit. Sorry for that. Yeah, you can export the keys, important, import, export keys, always check for that. And here, very important, the settings. I always use in my apps the day and night theme because it's also, you don't want to be blinded at night. And at day, you want to be able to read something. So in all of my apps, I use day and night. And on the bottom, you see you have the option to enable light client. I thought in the beginning, you always have to have light clients, but light clients, unfortunately, are in a very early stage and not really usable. They make your phone really warm. That might be nice in Berlin, but it's really bad here where it's so warm. So at the moment, I have it as an option, but later on, I want to have it on by default. But currently, it's not having a good user experience, and I want to get the user experience nice first. And later on, if light clients are really, really usable, then I make it on by default. Yeah, these were the problems with, but the Go team, big hands to the Go team because they are awesome. I report a lot of bugs, but they get fixed. Yeah, that's really good. And we need these light clients because currently the world leaders, it's crazy in what the world we are living in. And the problem is we have a lot of centralization in Ethereum also. And we need to fight that because all the infrastructure we have currently and we take for granted could be gone in a second. It's really bad. And also, please, I want you all to survive. Please install the offline survival manual, just in case, you know. Yeah, and also, please, everyone, activate LightSurf, because at the moment, light clients also suffer that there's no incentive structure yet, and people don't activate it. Please activate it on all your nodes so we have a better experience, especially on testnets. So I have to skip a little bit stuff. All the tokens I support ERC20, and all the token support is coming from my Ether wallet. If you want to add your own token, please make a pull request against this repository, and also a big shout out to the My Ether wallet team. It's just awesome what they are doing there. What you see here, yeah, clap for My Ether wallet, yes. Sorry. But we have to hurry. Yeah, we should clap longer, but we have to hurry. Here's very important. The keys are in the user data directory, and the cache has all the light client data. And you see how big the light client data is. Like, it's 500 megabytes. So you can safely delete light client data, but please never delete the user data because they are your keys. And I don't have them. I cannot secure them, even if you ask me. I have no chance. I don't have them. Very important where to get your stuff from. There's a trade-off between convenience, Google Play, very convenient, but very centralized and not free. And GitHub is just like a synonym, is also centralized, but I mean, it's always built from source. And something in between is F-Droid, also a really nice project. It's in between, basically. And don't get it, please, from, because I didn't get the ENS domain. It's a very sad story. There is Kotlin, like everything is written in Kotlin. There's Kotlin stuff emerging. I wrote a library, Etherium. It's a Kotlin Ethereum library, and I have to stop now. I have a breakout, and at Android Things, yeah. I have a breakout session at 16:50 in the breakout room, so I hope to add some stuff then there. Thank you very much. Here's a follow-up, Ligeti. Here's my talk. Okay.
Thank you, Marcus. Next up on stage, we have Jared Hope with presentation Status, Ethereum at the Edges of the Network.
Cool. Yeah, hi, I'm Jared. I am the main organizer and thought leader on an open source mobile Ethereum client called Status. Show of hands who's actually heard of us? Amazing. Woo. Cool. For those who don't know, Status is something like a hybrid instant messenger and mobile DApp browser. And really we have one goal, and that's to take Ethereum technologies and put them in the hands of people. What I love about the Ethereum community is we've taken this fervor for crypto, but we've tempered it with pragmatism. And this has made blockchain technology palatable for organizations, banks, and governments alike. However, this pragmatism has been somewhat of a double-edged sword when it comes to taking this technology and putting it in the hands of people. And I'd like to start off with a short story that I think illustrates this point. So, on October 1st, an autonomous community of Spain, Catalonia, held a referendum of independence. Leading up to the event, they used a superb decentralized file storage technology called IPFS to organize their votes. However, non-technical people were using a centralized HTTP proxy and accessed this information through the comfort of their own browsers. Leading up to the event, on the September 26th, I believe it was, Spain issued a blockade of 140 domains, one of which was this gateway. Politics aside, disrupting a vote shouldn't be that easy. At the same time, the Tor project saw a surge in the downloads of their messenger. This is the Catalans hardening their communications. And one of the many things we can applaud the Tor project for is that they understand they need to package and make their sophisticated software easy for the average user to use without compromising on the integrity of that software, because when push comes to shove, decentralization matters. And so how we package, disseminate, and present these technologies to the end user enables them in ways that we haven't been able to do before. And this is really the core problem that we aim to solve at Status. So, since last DevCon, we spent a lot of time thinking about the overall user experience and design of the perfect Ethereum client. And nothing matters more than that first run. Together with our community, we've discovered what we think is the typical emotional narrative that a new person coming into the crypto world is likely to experience. And on that first run, we want to make sure they feel safe, in control, not overwhelmed, while at the same time connecting them with their goals and allowing them to explore Ethereum how they wish. While at the same time, we don't want to overwhelm them or demand information from them unless it's absolutely necessary. For example, we don't need them to back up their key phrase until they actually have real value in their accounts. And at which point, backing up their key phrase does become completely vital, and they have a reason to do so. And so that's when we educate them. We're also introducing an omnibar into Status, which means that you can access anything you want to do with an Ethereum within just a few taps, whether that's accessing dApps, finding your friends, opening new tabs, or signing a transaction. We've also worked together with our community to develop what I think is one of the most visually stunning and intuitive wallet experiences that frames your digital assets perfectly. We've also wanted to make signing transactions as less intimidating as possible, while at the same time bolstering the protection against phishing attacks with a signing phrase of 3 words. While we were building out that signing phrase, we actually found out that many of our users want to store sums of value and control them from their mobile phones, which are much larger than what they would fit in their normal analog wallets. And we realized that a software key pair is just not going to cut it. So today I'd like to introduce you to our new initiative, which is the Status Hardware Wallet. This is an open source Java card that allows you to take the trust, safety, and security of a hardware wallet, but use it on the go. It has 2 modes of operation, the first of which you can sign transactions directly on the card of arbitrary sizes. However, this requires vendor-specific hardware, namely to support Ketchak 256 and proper EC point multiplication. It is in the 305 spec, but finding a vendor that properly supports it is somewhat an interesting problem. And also to support Bluetooth as another communications protocol aside from NFC and contact. The second mode of operation of which signs transactions generated off card. All signing is pin-bound. However, we do support key pairs and HD wallets, with the HD wallets having 2 extra features, the first of which is to store and export your Whisper identity, and the second of which is to actually make one derivation path pinless. And therefore, this account becomes balance-bound, but allows you to have frictionless transactions. But signing transactions doesn't really mean that much unless you've got someone to send transactions to or something. And so with Discover, we really want to connect you with people and dApps and communities. So we're solving the search problem in a decentralized manner. And this is what we do with Discover. Discover is basically a naive epidemic protocol in which users publish public statuses with the use of hashtags, and this is propagated to their friends. Every user then collects a cache of messages that they've seen, and periodically they generate a preference list and then share that subset with all of their contacts. This preference list is generated by a bunch of different weighting factors. For example, if they're mutual friends, that they're like how recent it is, if they're online. What was the other one? There's a bunch of others. Oh yeah, like if they've been chatting with that person or interacting with that dApp for a long period of time, and if they trust them. And so in Status, we're actually going to be building multiple layers of trust. And this is going to be the first layer, which is basically automated, because when a status is shared, it is signed by the propagator. This allows us to build chains of propagation to see how far something's propagated, who by, and the same with moderation and reporting. So, as you may know, Status is built entirely on Ethereum protocols, and therefore we use Whisper as our messaging transport. Whisper has amazing privacy features built into it. However, it isn't without its problems. And one of these is essentially both peers need to be online when communicating. In normal usage, a sender will send their message to a recipient. It'll bounce around the network, eventually arrive at its destination, and this recipient will send an acknowledgement of that message. However, if the recipient is offline, the sender will send out a message and periodically resend it, but the recipient is both unaware that they've received a message, and they need to come back online and wait for the sender to rebuild their chat history. So we are introducing status nodes, which act as offline inboxes for Whisper, as well as helpers for external services, such as push notifications. It basically works on a promise challenge deposit, and it allows the sender to send these messages out. They get collected in these nodes. The recipient can be then informed, come back online, and rebuild their history with a node, even if the sender is not available. Well, you may be wondering, well, who is going to run these nodes? And of course, if somebody has a server, they can run it in a headless way. But really, we think we can do a bit better than that. And so we actually think you can do it, because we are actually expanding our platform reach. So we're not targeting Android and iOS anymore, but we're also targeting Linux, Mac OS, and Windows. And so with this, we're going to make it dead easy for you to set up a status node and integrate with external services, whether there are other chat protocols or push notifications. And at the moment, we have an internal friendly competition. We do build status on a single code base, and that rests on top of React Native. So on the more developed version there is actually using React Native Web. And the other one is another fork of a canonical project where we're actually building React Native from the ground up for desktop based on Qt. And currently we have 60% component coverage on that. So exciting times for us. In addition to this, another problem that we've really faced in growing our organization is that the talent pool in the crypto community is exceedingly small. So we want to take the strengths of being an open source project and help incentivize contributions. And this is what we're doing with Open Bounty. This allows you to take any GitHub issue and create a bounty for it that anyone can then contribute to, whether it's ETH or any ERC20 tokens. But we're actually taking this a step further from just the general mechanism, which we've had for a while, and we're actually building out our talent scouting and human resources around this, so we can help other decentralized organizations build their software just like we are. And in fact, we also have a $1 million bounty coming up to help other organizations get involved. So please come join us at openbounty.status.im if this is interesting to you. In terms of our next steps, well, now we need to focus on optimization. We're deploying our security audits, which allow us to move into production. We're also supporting identity standards, and we're experimenting with the Swarm messaging service, PSS, for more convenience. So that's it from me. Thank you so much, and I hope you're all using Status.
Hello, hello. Okay, next up this morning we have Felix Lange with Evolving Dev P2P.
Check. Hello, guys. Oh, thanks. Yeah. Hey, guys. So many people here. Yeah, I'm Felix. What is it? Should I use this? Okay. Hi, guys. So I'm Felix. I work for Ethereum Foundation on the Go Ethereum client. And my role there is mainly bug fixing and feature development, but I guess there's a lot less time for new features lately. And my passion in this project has always been, like taking care of the way that nodes talk to each other. And this is also what I'm talking about today. So Dev P2P came into existence, I guess, about 3 years ago, and at the time, the vision was to, as you can read there, provide a lightweight abstraction layer that provides low-level algorithms, protocols, and services in a transparent framework. So, like it was a pretty grand vision. In 2017, though, Dev P2P is just this thing that you need to implement to talk to the Ethereum blockchain. And it's part of all known Ethereum implementations. So all of the 6, 7 implementations that are live on the network have an implementation of Dev P2P and all of the stuff that's in it. And there have been very few actual protocol changes since 2014. So if you wanted to, you could count them on one hand, basically. Dev P2P has a bunch of elements to it. So the first one is the node discovery protocol, which is a way of finding other nodes to talk to. Then there is the RLPX transport protocol, which is what is spoken on the TCP connections between nodes. And Finally, there's an application layer protocol that sits on top of the RLPX transport protocol, and this one is somewhat confusingly also called DevP2P. So both the overall system and this particular protocol are called DevP2P. Let me just walk you through the protocol that's in use on the network today, and then maybe we'll come to the part that can actually be improved about this. So this dark circle there, that's us. So we're a node that wants to connect to the Ethereum network. So how do we do that? So we'll join the DHT first, and the DHT is basically the part that is this thing where you can find the other nodes that are on the network. Yeah, so there are some other nodes. They're also registered there. And then basically we walk the DHT at random to find someone to connect to. And then we try to establish a TCP connection to them. And the TCP connection might actually fail, so this happens quite a lot because the node, might no longer be live, or, it might be too busy handling other connections. But let's just assume that it works this time. So once the connection is established, we exchange capabilities with the other side. So basically, this is now the part where the DevP2P application layer kicks in. And in this particular case, we see that the shared capabilities there's just one shared capability, and it's the ETH capability in version 63. So now once ETH version 63 is running, we can exchange information about the blockchain that we're both on. And once that matches, we have a new peer. Yeah, so that's the current system. And it's not super efficient, and well, there's a whole bunch of details that I haven't really talked about, but I guess you kind of get the idea. So what can we improve about this, though? So first of all, it's kind of annoying that there are so many round trips just to figure out whether someone is on, the right blockchain. I mean, I guess that's kind of obvious. And then it would be really nice to just sort of know that, before even connecting, maybe. And then another issue is that the whole system is basically frozen. So making any change to any of the protocols requires really tight coordinations, requires implementation consensus, and any change that we make needs to be backwards compatible. And to achieve upgrades at all, what we've done in the past is we've made all the upgrades backwards compatible, and we've tied them to Ethereum mainnet hard forks, because well, everyone has to upgrade their node anyways, and then once the hard fork is successfully launched, we can start phasing out the old stuff and just, only speak the new protocol. But, hard forks don't happen all that often, and we'd rather, make changes on an accelerated schedule, but it's really not that possible. And then finally, because node discovery only relays information about the RLPX protocol, there isn't any sort of room for experimentation, because, well, we're essentially stuck with RLPX and the crypto system that it uses. So improving these things is the node discovery version 5 effort. And with node discovery version 5, we want to make 2 changes in particular, or rather we want to achieve 2 things in particular. So the first one is we'd rather, be able to find nodes more efficiently. And then the second one is we'd rather know more about those nodes before we even connect. So the first part of our solution to these issues is called ENR, which stands for Ethereum Node Records. So earlier in the V4 overview, you saw that the DHT holds all those eNode addresses. And an eNode address is really just a public key, an IP address, and 2 ports. Ethereum Node Records can hold arbitrary information about a node. So that's the main difference. So this arbitrary information, that can be information about the capabilities of the node. It can be information about other transport protocols spoken by the node. It can be initial key material for those transports. Anything really, as long as it fits into 300 bytes, we're basically like almost anything can be relayed there. And the limitation of 300 bytes is important because ENR is a separate format, a separate spec even, and is not at all connected to the DHT. So you can relay those records through any other means if you want to, including, say, a DNS record or something like that. And then finally, node records are signed and also versioned. So if you have two versions of a record that describes the same node, you can determine which one is newer, for example. And we think that ENR is a good solution for the transport legality problem because, again, information about arbitrary transports can be relayed through this protocol. And, well, yeah, because there's just a lot more room to put, information about anything. So we still need implementation consensus, though, because, in order to be able to talk to everyone, everyone kind of has to agree on, what the language is that they're speaking to, that they're using when speaking to each other. And it is very likely that for a considerable amount of time, the lowest common denominator will be RLPX. But eventually, once ENR is launched, we can actually try out different transports, find a viable alternative, and then, maybe like at the end of 2020, like delete RLPX. So, in order to get ENR launched, though, we need to upgrade the discovery protocol. This is something that needs to happen once, and it will be a backwards incompatible upgrade. So likely, the way this will work is that the discovery version 5 DHT will be a totally separate DHT that will run in parallel to the current system. And because this is kind of a unique opportunity for us, in addition to just including support for ENR, we want to make a bunch of other changes to the protocol. In particular, one problem that the V4 discovery protocol has is its reliance on absolute time. So maybe some of you have actually experienced this. So if your clock is off, let's say by 2 minutes, you won't really be able to connect to the network. And we've worked around this by alerting users when their clock seems off, but that's a really ugly workaround, and we might just fix it in the protocol this time. And then with many of the nodes in the DHT, you'll find that the information that's listed there isn't very accurate. So you might not be able to connect to this node at all, even though it's listed there. And in V5, we want to introduce this concept of endpoint proofs, where the DHT ensures that if a node's record is listed in the DHT, there's a pretty fair chance that you'll actually be able to talk to it. And then finally, we have another improvement, which is also which can be considered an extension of the DHT protocol. And this one is about finding nodes more efficiently. So in a classical DHT, so to say, the DHT is an index of nodes by their public key. And it maps public keys to node endpoints. But the nodes in the DHT, though, they're not in any kind of useful order. So you'll find an Ethereum mainnet node next to an Ethereum classic node, next to a node that doesn't really participate in the Ethereum blockchain at all. And there isn't really an efficient way of knowing about just the nodes that you care about. And contrasting that, the topic index that we have in mind is sort of like an index of all the nodes by the topic or the service that they are providing. I don't have a lot of time today to really go into the detail of how this works, but I can give you an overview of the design constraints that we set when making this protocol. So the first big constraint that we had is that we don't want to split up the DHT, because with DHTs, bigger is better, right? I mean, fundamentally, the security of a DHT depends on the number of participants in it. So you would want to always have a very large number of participants. And another design constraint we had is that these topics kind of have to scale to an arbitrary number of participants. So there might be topics that everyone is advertising, like everyone who's in the whole network. But then on the other hand, there might also be topics that are very small and only advertised by, let's say, 5 or 6 different nodes. And these topics shouldn't really compete with each other, so you should be able to resolve both equally quickly. And then finally, with all of these systems, there's always like the danger of, people spamming it with like arbitrary registrations that nobody ever cares about. And those particular registrations should not drown out, the actual useful ones that you really want to see. And to combat many of these attacks, the topic advertisement protocol includes this thing called advertisement inertia. So this is really just, an artificial delay enforced by the protocol before a certain registration for a topic can go live. And we feel that, in addition to maybe reducing misuse of this, in addition to, combating these attacks, this also reduces the misuse of the topic index, because fundamentally, topics are meant to be used for announcing big decisions like way ahead of time. And those big decisions can be something like which blockchain you're on, or which shard of the blockchain you're on, or, well, things like that. And not so much like, let's say, the URL of a video chat that, you're just starting. So we really want those things to be used, like for facts that will have, a bit of a bigger meaning. So to recap, the node discovery version 5 is about finding nodes more efficiently and knowing more about those nodes before we connect. A prototype of this system, although without the ENR, has been in use by the Geth-like client since early 2017. We're still working on the EIPs, so nothing is published yet. But once it is, we will have like a separate spec for ENR, a document that goes into detail about, like the semantics of the topic advertisement protocol, and finally, a description of the actual wire protocol that's spoken via UDP. But there's really nothing set in stone yet. So if you feel like, there's a certain change that absolutely has to be made, or a certain feature that should really be included or not included, just come talk to us. That's it.
Hello. Up next on stage we have Power Blitzer with EVMC Portable API for Ethereum virtual machines.
Hello, everyone. Yeah, so I'm Paweł Belica, and this talk will be about EVM and EVMC, which is a portable API for Ethereum virtual machine. I'm a software developer. I'm specialized in C++, and currently I'm working mostly in the CPP Ethereum project, and I also I'm the author of EVMJIT, which is alternative EVM implementation that translates EVM bytecode to native machine language, and I also try to come up with the API for EVM that is called EVMC. So this talk will have two parts. First one, I would like to explain what exactly am I talking about, And what I mean by EVM API and EVM interface. And in the second part, I would like to show what have been done so far, what we want to do in the near future, and explain some design decisions we made so far to be able for you to better understand why things look as they look at the moment. So EVM, the Ethereum virtual machine, one of the most important components of Ethereum software and Ethereum ecosystem. So it's, in short words, virtual machine that actually can execute small programs or small scripts called smart contracts. And yeah, where it is. Every Ethereum client, at least full nodes, have EVM somewhere inside. Usually there is one implementation of that, but we have some examples where EVM clients can actually have more of them. And CPP Ethereum is one of the examples here. But the problem I would like to address is the fact that EVMs are somehow embedded inside the client. You can have more or less indirect access to it, to EVM, through JSON RPC, some test RPC systems, VM tracing, storage, backlog, and so on. But what I try to address is I would like this this composition to look more or less like this one. So this thin layer that actually connects EVMs to Ethereum clients to be very well specified, very well documented, and to be also usable in from different programming languages. And also, what we can add to this scheme is to be able to actually plug in the same EVM implementation to different clients. Okay, so EVMC is one of the possible solutions to this problem, and it's exactly what I meant before. It's EVM API that uses C language to connect these two now separated components, the EVM Ethereum virtual machine, to be connected with Ethereum client. And why C language was chosen? Not because it's the most beautiful one, but it happens that C is actually accessible for many programming languages. The obvious examples are C and C++, but for many popular languages that are around, you can actually at least use some C libraries and execute functions from C libraries from that languages. I tried all this stuff with Go using the CGO tool, and also in Python using CFFI library. But I'm sure there are other examples when you can at least use C libraries in more high-level, more abstract languages. And second important part of that is we want to have polymorphic interfaces there. So we would like to be able to use to switch between different EVM implementations and runtime. Not that we want to build a client with this one and decide on the build time what actually implementation we'd like to use. Yeah, we want to have a switch that user can actually use to decide what kind of backend they want for its task. And third important part we took account of to make some design decisions is composability. So the composability means actually we can do something like that. When having some concrete implementations of VM, we can add more and more layers on top of that actually delegate the execution to the lower layers. But on the upper layer, you can make some additional decisions where actually you want to send your code to. So, for example, if we consider interpreter and JIT-like EVM, you might want to actually have a top layer that actually decides if the code should go to the JIT one or to the interpreter one. And the top layer can actually, for example, count the number of executions of particular code. If we have some hot code that is executed in many transactions, we may want to actually translate that using the JIT EVM to some native machine code and speed up the execution. But that may not have sense if the code is not frequent enough to actually pay the cost of overhead of doing the translation upfront and not having, may not make a lot of sense. The second example of such composition can be having actually different languages in smart contract. If we consider the proposed EWASM and EVM 1.0, we can just add very simple layer on top of that actually can recognize if the smart contract uses the WebAssembly-like language or EVM1 bytecode. So how actually this EVMC looks like? This is actually the single file, a single C header file, and includes declarations on functions and structs, and also all the documentation is this file in form of comments. So this is actually the only source you should care about, and I paid attention to actually have good enough documentation to understand how it works, just reading the single file. And at the moment, this is part of my EVMG project, where as long as I'm experimenting with that and the API is not finished yet, it's included in this project. Okay, so the whole design has some kind of two parts, two sides, and one is related to the client side, and one is related to the EVM itself. On the client side, what have to be done? You need to implement some context class, and context class provides a virtual method and can answer questions coming from EVM. And these questions are something like, get me the balance of given account, or get me the storage at given storage slot for given contract. All this information cannot be provided to the EVM upfront because we don't want to send the whole state to the EVM to execute smart contracts. But DVM need a way to actually extract this information on demand. And on the second side, on the EVM side, there is EVM class. And EVM class, it's quite simple. There is a way to actually construct the EVM instance, and there is a way to destroy it. And the core function is actually execute function. When the information what is to be executed is encoded in a message object, and also the context is provided for the execution. And EVM uses this context interface to ask for more data if needed. So in case you would like to implement new client, but you don't want to in the same time implement EVM there, you would like to use some of EVMC compatible EVMs available. What you have to do, your job is to implement the context class, and there are 8 virtual methods that have to be implemented, and you have also encode your information what to execute in the message structure. And if you would like to, for example, implement the EVM, but you don't care about the rest of the Ethereum client, like network stack, storage, database, and so on, all you need to do is to implement the create and destroy pair of functions and the execute one. So, not to be confused, this design operates on the object-oriented concepts, but on the way you will do that, you will have to translate it down to the C, so it gets more obscure and complex. So what we have so far with this. So as I mentioned at the beginning, the C++ client have actually two EVMs, and one is classic interpreter, and it actually does not use the EVMC, but we plan to do it in the near future. But EVM JIT, the JIT-like EVM, uses the EVMC interface, and it's compatible with the recent hard fork of Byzantium. There is also the Hira project, that a prototype of Ethereum client with EWASM backend, and there is also a prototype of EVM implemented purely in C language. I also prepared some time ago a prototype of GEF with the EVM JIT plugged in, and the Python client with EVM JIT plugged in. This still needs some work, and it requires updates to the current status of the code, but it's quite fun to play with that. And what we want to do next. The missing piece of EVMC API is VM tracing, and this is a showstopper for a moment, because we cannot replace existing VMs completely, because this missing feature is important in other places. We would like, if this is in place, we would like to move the CPP interpreter to use the EVMC interface as well. And I also plan to release experimental GEF with EVM JIT as a virtual machine there. Recently also someone considered to using this interface together with fast testing project. Okay, that was all from mine. Thank you for your attention, and in case some questions, I'm available for for whole Devcon around. Thank you.
Just come up. Okay. Is this on? Hello? It's not on? Hello, it is now. Okay, up next we have Dr. Greg Colvin with the EVM, cleaner, meaner, and closer to the metal. That's quite good. I know.
Really? Do-do-do. Don't clap yet. We're getting the equipment set up. I'm Greg Colvin. We discovered we can't play videos off the USB stick from the back, so I have to control my laptop from up here and hope it all works. Good morning. That's sort of pretty, but it has nothing to do with what I'm going to talk about. Yes. This is highly advanced technology, highly skillful technologists. I think I was supposed to be here last night so we could work this out, but our dinner was like an hour late, so they kept bringing us free beers to placate us. I usually drink 1 beer a week, so 3 beers in one night is like a bender for me. No, that won't help. It's live. Okay. They've put it in a different mode. There's a little clicker. Okay. I'm Greg Colvin. I spend my time for Ethereum, working on the virtual machine, working on improving its performance, and working on designs for possible successors to what we have in order to solve some of the performance problems that we're running into. If this works, there will be another slide. How about that? The first problem you run into in any sort of optimization work, according to my old friend Jerry Schwartz, is one, all benchmarks are bogus. You'll never have a set of benchmarks that actually represents the real world. But if you don't have benchmarks, you will just go in circles. You'll never make progress. So the benchmarks I'm working with are a few algorithm kernels that are relevant to what we're doing. RC5's an old and useless cipher, but it's a good example of a cipher that uses a lot of 32 and 64-bit arithmetic, a lot of complex logic. And Blake 2B is still an important hash function. It's also a lot of 64-bit logic. Blum Blum Shub is a cryptographic random number generator. I think it's one of the slowest in the world. It operates on big registers, so we can use the 256-bit registers of the EVM effectively, and ECMAL also can use big registers effectively. And then I have a few tests of individual EVM operations, and those are small EVM assembly programs to try to isolate individual operations. And this is a graph of what I got with the whole thing. And it's a bit complex, but what you can see down along the bottom is the different benchmarks, and along the right are the first three are some major clients. EVM is our Go client, Parity is a Rust client, Ethereum is the C++ client. The rest aren't clients yet, but EVM to WASM is part of the WASM research. It's a program that takes EVM code, translates it into WASM code, and then I fed that to Google's V8 engine, which generates assembly code. EVM JIT, Pavel was just talking about, it generates assembly code directly from EVM code. And then the native C++ is I rewrote the benchmark programs in C++ instead of Solidity or EVM assembly and compiled those to assembly. So pretty clearly the C++ wins the race. And pretty clearly exponentiation is pretty hard for everybody, which isn't surprising. But it's a little concerning. There might actually be possible exploits by writing contracts that do exponentiation and get charged only a few gas, but take a whole lot of time. And RC5 looks pretty hard because RC5 works on dynamic shifting, and EVM does not yet have a shift operator, and so it gets imitated with exponentiation. And in between, things are relatively regular, and the speed you could actually predict by the language that the client is written in. Whoa, where did that come from? Next slide. I can't see the screen with these glasses on. So to simplify it, this is looking at one angle. It's the harmonic mean of the performance of each client. And it shows pretty much the same thing. So clearly the interpreters are not as fast as going straight to machine code by any route. And clearly some interpreters are better than others. But they've all been good enough so far for our purposes. And of course, I love car races as examples. Last year, somebody in the audience shouted out that instead of using classic cars burning tons of gasoline, I should be using a Tesla. And Teslas are nice. Is George Hallam here? Are you here, George? George would agree that rather than a Tesla, this would be much cooler. This is a '68 Mustang hatchback. Under the hood is actually some powerful electric motors, and the trunk is full of lithium-ion batteries. And if this works, where's the button? We will see how this does against a Tesla. Is there any sound? No such luck. But there goes the Mustang. Tesla doesn't have a chance. So, a digit's missing, but after a quarter mile, it had gotten to 140 miles an hour. That's a lot. So what keeps those interpreters from reaching native speed? And the first answer is they're interpreters, so they've got that overhead. You can work hard, you can reduce the overhead, but generally you can't do better than about 3 or 4 to 1 compared to native code. For our particular interpreter, the 256-bit registers slow us down because real hardware has 32, 64-bit registers, and the unconstrained control flow hurts us a lot, and I'll get to that. The 256 hertz, if you remember, grade school math, multiplying, 2 numbers is pretty easy. You can do it in your head. If you have 4 numbers, suddenly it gets a lot harder, and it's quadratic, so it gets worse and worse. 256 squared is a lot. Control flow. The jump operator in EVM, go-tos are considered harmful, but at least, if you say go to label, it will go to one and exactly one label. In the EVM, you say go to whatever's on the stack. So there's no way of knowing often statically where it's going to go. So you can have a nice little program like this, and F calls G and H and returns, and it calls I and returns, etc. Nice clean structure, no trouble to understand static analysis, anything, no trouble. What's it actually look like to the EVM? That's what it looks like to the EVM. So if you're trying to do formal analysis, if you're trying to write a compiler, if you're trying to do anything with it, again, the number of paths goes up quadratically, and you're in trouble. Because pretty much if you can't do it in linear time, or at least n log n time on the blockchain, at deployment time or at runtime, you can't do it. So how do we do better? Well, EVM JIT is already doing better. I won't back up, but if you look at the slide, the EVM JIT is actually pretty close to the native speed. It does very well on the wide arithmetic and not so well on narrow arithmetic and complex logic. But it's a very good JIT. I've told Pavel he gets to be the electric fox. He's tired of these little 3 and 4 letter names that don't mean anything. This is a racing team out of Latvia. That's a completely electric dragster. And here it is winning the European world record. There it goes. Drag races are fast. It's not impressive, is it? It's over. Hello? 275 miles an hour. Just a few seconds. Love these things. So we've got 2 research programs that have been going on how to improve things. They've been nicknamed EVM 1.5 and EVM 2.0, which doesn't really mean anything except those are the nicknames. And for 1.5, that's a suggestion to extend the current EVM by adding new opcodes and requirements. So we forbid those unconstrained jumps. We will not allow you to do that. And We then have to provide a way to do the things that you otherwise do with those jumps. So there's opcodes for subroutines, and then we've got to get away from having nothing but 256-bit registers. So we've got opcodes for native scalars and opcodes for SIMD, because real hardware has all this silicon devoted to SIMD registers, and if you go to Google and type SIMD crypto, you get a lot of results. So it would be useful to make that hardware available. And at deployment time, there's a validation phase that goes through the code and makes sure that it actually does follow the rules. What a concept. And then 2.0, well, gee, it provides opcodes for structured control flow. It's stricter than 1.5. It actually looks like a high-level language with if-else and such. And it provides opcodes for native scalars. It's SIMD the SIMD's coming later, but there's a SIMD proposal. And it also has a validation phase where it validates control flow and stack discipline and type safety. So they're very similar at that level. So we've got some technically very, very similar proposals. They both provide for very fast compilation to native code. It could be done as a JIT. We've come to realize Ethereum cannot do JITs. They are actually exploitable. That is, if you find or write a contract which takes a long time to compile with a JIT, but requires very little gas to run, and you start hammering those contracts, you can do a really nice DOS attack. So if you're going to do any compiling, you've got to do it up front at deployment time. And Martin's notion of transpilers, I think, is very important here. 1.5 can be transpiled to 2.0. 2.0 can be transpiled to 1.5. 1.5 or 2.0 can be transpiled to 1.0. Either of them can be transferred to the JVM. You can make up new ones. Pretty much, you can compile any VM you wanted to some other VM. And he also has a notion of gas injection. So you put little pieces of code into the right places to count the gas. And what this means to me is it doesn't matter what execution engine a client chooses. Because on the blockchain, you can put a contract that translates into that execution engine. So these can be completely independent choices, and we could actually choose to support a number of VMs if we wanted to, and independent parties could decide to support a different VM, put a transpiler on the blockchain, and away they go. Gee, I'm almost out of slides. And there's no sound. That's really too bad. So what is the big deal about native performance? And what's the big deal about being lean and mean and close to the metal? Well, we saw the electric dragsters. Here's like a real top fuel dragster. They run on a mixture of diesel fuel and nitromethane. And just about a month and a half ago, not too far from Ming's place in Michigan. This guy got the world record. And it's over. 338 miles per hour in a quarter mile. These guys pull about 5 or 6 Gs, which is about the same as an astronaut taking off in the space shuttle. But there's a problem with going fully native. In the SIB world, we call it undefined behavior. Hello? No, that's the last. Come here. Okay. Play, play. There it goes. What's going on my screen? We'll try it again. Doo-doo. The driver actually walked away unscratched. I love this guy. We'll give you one more. Boom. And it turns out I'm done. So. I knew it. Audiences love explosions. I'm done.
Casey, come introduce.
testing. This is the evolving the EVM panel. Hello. Works. Hoo-hoo. Find a seat, panelists.
This is really silly. This is hopeless. We're going to sit on the floor along the stairs. This is ridiculous.
You want to sit there?
Yeah.
Hey everybody, I'm Casey, and I asked to moderate this panel because I've been working on EVM and EWASM lately, and I know there are no other experts besides these panelists. So you saw Martin's talk yesterday on, well, it was on Crimea, but it mentioned the precursor to Crimea, which is EWASM, and that started in December 2015. By the summer of 2016, the first commit was in April, but by the summer there was a pretty working prototype for the EVM to EWASM transpiler. Then, so that was EVM 2.0. So after the 2.0 proposal came the 1.5 proposal from Greg and Pavel. And you just saw Pavel's talk earlier about EVMC, which is sort of the API to plug in and be able to swap between EWASM and EVM 1.5. And then came, earlier this year, was Julia. Yesterday also we saw Alex's talk about Julia, which he and Christian designed to upgrade Solidity and be able to make Solidity target the EVM 2.0, the next versions of the EVM 2.0 and 1.5. And then, and since then, also Pavel has made a lot of progress on the JIT VM. So it's sort of been backwards, where first EVM 2.0 was proposed, then more progress on EVM 1.5. I hope this makes some sense, so I think I'll ask our panelists, what is what is EWASM and what is EVM 1.5?
Well, when I arrived, I guess EWASM had made some progress, substantial. And a few things struck me. One is people were sort of excited because, gee whiz, you could run, C++ contracts in EWASM. And as a C++ expert, I said, why on earth would you want to write contracts in C++? Haven't people lost enough money on the blockchain already? And the other thing that struck me was, why on earth would you want to hand over to an outside committee the definition of anything to do with the core consensus protocol? And I looked at the current EVM and said, there's an awful lot of white space for more opcodes, and this thing's not broken, it needs a little work. So I set out to say, what do we need to do to this to bring it up to modern standards and make good use of modern hardware? And So I got to work on that, and I got a lot of help from other people on the C++ team. The documentation would not have happened without Christian. So the team put a fair amount of work into that. We've got a couple of EIPs. Martin has put a lot of work into the EWASM proposal. So they're sitting there, and we'll need to make some choices, and we might throw both of them away and say, okay, we've learned a lot. What should we actually do? We might choose one of them. We might stick with what we have and ask, can we advance our compiler technology to compile what we have into code that runs better, and Pavel can speak better to how possible that actually is.
Yeah, I would be very happy to have any of these, but to add it more constraint to the control flow would help a lot there, and I believe we can do much better in JIT-like EVMs if we have that.
But just a step back, so last year when you came around and EVM 1.5 came around, it was still in a point of time where WebAssembly was not finalized at all.
Right.
And there was no knowledge, at least we didn't have any knowledge, when it's going to be finalized.
Yeah, there's no idea.
And since then, this year, the first version came out. So that problem went away. And like back a year ago, we had no idea when it's going to be finalized and how it's going to look like when it's finalized. So that was a big concern. And I think because of that, EVM 1.5 made a lot of sense to maybe bridge the gap or have like a backup plan. Assuming that EVM 2.0 would be finished in time, but we cannot release it because the WebAssembly isn't finished. And then if we could finish EVM 1.5 quickly enough, it could be a good bridge between the two. But that problem went away today, earlier this year. So how do you feel about the brokenness of EVM since? Did anything change?
I actually think EWASM's going to die.
Why do you think that?
Because there's been so many attempts to get a binary format running in browsers, and they've all failed.
You're saying WebAssembly is going to die, not...
Yes. WASM's going to die. Whatever I said, I don't know.
That's a bold prediction, but maybe we can step back and say, what are the problems with the current EVM 1.0? I mean, one problem is that the gas limit in each block is not enough to do everything people would like to deploy contracts to do. Because one example is the Blake 2B precompile. There's a proposal for these native precompiles. And precompiles solve the problem of contracts that people would like to deploy, but they might take 100 million gas when the current block limit is the current block gas limit is 6 million gas. So how does EVM 1.5 or WebAssembly solve this problem?
Well, WebAssembly would allow you to just compile code directly to WebAssembly, so you most likely don't need native contracts because you would just write them in WebAssembly.
Yeah, it's partly gas, but it's partly just that it's too slow. Pavel was working, I remember, on one of the precompiles that you were like pushing all the compiler flags as far as you could and trolling through multi-precision libraries to find one that was mostly in hand-coded assembly. We just can't get enough speed out of the VM for these precompiles.
And how is 1.5 and 2.0, how are those becoming faster than 1.0?
This is back to my little grade school example. You do a multiply and you're doing one instruction on a 64-bit pair of registers as opposed to, long division or long multiplication on a collection of registers.
I think the current issue we have is quite big difference in terms of speed comparing to native code. So we cannot actually effectively encode the algorithm we want there, for example, some hash functions, and that makes them, if you like to implement them in pure smart contracts, that make them quite expensive. And you have to pay for that. You have to pay a lot for that because it's just the current EVM is not capable of express enough to have comparable speed comparing to native code. And I believe that's what, for example, WebAssembly gives. Like, it's at least comparable. Like, if you implement the same hash function in C and WebAssembly, at least you have comparable of them, and not having like 10 to 100 times slower performance.
But actually, if you take a step back to like the first version of EVM and look at why do we have, or why did we have an identity contract just for cheap memory copying, that maybe shows that we didn't have everything thought through properly, and we started to introduce these precompiles, especially the one for copying memory. That means loading and storing memory was too expensive, yet we still wanted to do it, so we introduced the precompile. And the other bigger issue, which Greg mentioned several times already, is the bit width. Everything is 256-bit. And there was a proposal even before the 1.5 to have 64-bit arithmetics in EVM. You have folded that into the CMD proposal, so it's still there. But if we just look at these two problems, that it's quite wide for arithmetics, and we started to introduce all these precompiles just to get around that, probably shows that we didn't figure out the prices properly. And with WebAssembly, as Pavel said, it resembles the instructions much more closer to traditional computers. So there's probably much easier way to figure out what the real cost for those instructions are. And by figuring out the real cost, we can probably avoid having precompiles.
That would be nice. It's worse than 10 to 100. My graph was scaled by square root, and the slowest exponential operation compared to the fastest native code was 10,000 to 1.
But that was on EVM to WASM, right?
It was actually Go versus C++ compiled straight to assembly. So,
well, another advantage of, another motivation for the EWASM proposal was to be able to write contracts in other languages that target WebAssembly as a compilation target versus only targeting EVM. So we have the EVM to EWASM transpiler as a prototype. We don't yet have the EWASM to EVM transpiler, so the reverse, which would make the EVM 1.5 proposal equivalent to almost the EWASM proposal. Because then you could still write contracts in languages that target WebAssembly, transpile those to EVM 1.5. I've asked before what would it take to write the EWASM to EVM 1.5 transpiler, and Greg said it would be easy. Martin said good luck.
Yeah, good luck.
You told me it would be easy.
It's not impossible. I would never say it's impossible.
You said it would be easy. You told me it would be easy.
I don't know, honestly. It's going to be some work.
It was on a fire escape in Berlin. I mean, but
was I sober?
I don't know.
And also, one of the motivations for just skipping EVM 1.5 and because the original proposal was just going straight to 2.0, the EVM 1.5 proposal came later. And one of those reasons was because, well, it must be hard to write a JIT compiled VM, and then Pavel wrote a prototype of a EVM JIT VM. Was that easy, Pavel?
So actually, the prototype of that, it's still a prototype. It was done even before the launch of Ethereum. It was one of the performance benchmark project that we want to have to actually assess what can we do in the future in terms of smart contract performance. But yeah, it still struggles with some cases, and as I said, we can do much better in this case. And the required step is at least this control flow restrictions and subroutine support directly in the EVM bytecode. That would allow even more optimizations. But on the other hand, like JIT compilers are hard. I mean, the network consensus depend on that, and like the risk is like we might get hard, or it might be never finished in terms of removing bugs and finding edge cases, because that's much more complex construct comparing to interpreter.
I mean, another problem with just-in-time compilers is that I'm not sure if there is a just-in-time compiler that provides a fixed upper bound in terms of resource consumptions, and this is a very important guarantee that we need in order to do the gas calculations properly, right? I mean, usually just-in-time compilers generate code that is faster and takes less resources, but we don't have a guarantee, or do we?
Well, as I said, we can't do a JIT. It's exploitable. It has to be a compiler that runs at deployment time, not at runtime. Which means it can be a full compiler, depending on how long we want to take to load a block. And my understanding is storage is the main constraint there anyway. But I mean, I remember in my testing, I came up with one performance bottleneck, and you said, it's not a priority, I don't think I can get to it. And the next day, you had it fixed.
Yeah, this is a bit different issue. So in Ethereum, we actually care about the worst cases, because this is what the cost must be for, and so this affects more complex optimizations, but also the big integer libraries that actually try to squeeze the easy cases first. But this is not what we point to. Like, we don't care if we can divide quickly for small numbers, because what we care is to have the worst case covered. So yeah, that would be much more difficult to control that within the JIT, because it's like you have the big, at least in the EVM JIT that depends on LLVM, you have a big backend library that does that for you, and it's really hard to tell what it's actually doing. But yeah, I guess there are different approaches to that. And for example, EWASM has some JIT prototypes that are not depending on LLVM.
And of course, one of my bigger concerns is not technical. Either of these programs technically does the job. I'm much more concerned about who controls the specification. And I really believe that the Ethereum community should completely control that specification. The web browser space is not the Ethereum space, and I would not want to get wedged with the WASM group moving in a direction they need to move, and us shaking our heads and going, no, we don't want to go in that direction.
Yeah, I disagree with that because I think I much rather, it's much more pluralistic to go with a larger community, a larger body of people standardizing and coming to consensus on a virtual machine instead of just using a virtual machine that can only be, or was created to only be used in one specific use case. And if you look at the browser use case, it is very similar to the blockchain use case. We need secure, portable, and size-efficient bytecode, right? It's the exact same concern we have in the blockchain space.
Technically, I agree.
And furthermore, like, it's open to participation. You can go to the WebAssembly community meetings. You can voice your opinions. You can submit proposals on GitHub. It's very open, and it's easy to get involved. Within the blockchain space, I know of at least 3 other blockchain projects outside of Ethereum that are already prototyping and actively have WASM running in their systems. So we're seeing a lot of momentum, I think, pick up around it. And I think that's sort of just going to be the way it is because, like, once we start to have consensus around a VM, everyone's just going to be the obvious choice. Everyone's going to use it, and it's going to be a recursive feedback loop, right? It's going to be a feedback loop where since there's more people using it, we're going to get better tooling for it faster, we're going to get better implementations, etc.
But it's not like, hypothetically, if we introduce EVM 2.0, it's not like that WASM would introduce a new update and that magically would work on Ethereum. As you mentioned in your talk, both 1.5 and 2.0 have a verification code which has to run prior deploying the contract. And that verification code verifies the, according to the eWASM specification, which is the current list of opcodes in WebAssembly. So if they introduce new opcodes, they wouldn't work without us making the decision that we want to support them. And so I don't really see that as a risk that we would be exposed to random new instructions being supported by Ethereum without our review first.
No, I'm more concerned. So we come along and there's an issue with WASM. I mean, bugs show up in specs, or if not a bug, an ambiguity. And we resolve it one way, and it works for us, and we can't wait. If something's a little weird in a browser, it's not a big deal, and the committee will get around to it. But if there's anything that breaks consensus, we have to fix it immediately. And then eventually it gets around to the committee, and they go, no, we don't like the way you fixed it, we're going to do a different fix. And I just feel like over time we will wind up forking away from that standard, and we will lose these benefits of shared design and tooling anyway. In fact, we're a fork to begin with. We're a subset. So I spent a couple weeks trying to get C++ into WASM. I succeeded, but it wasn't easy. And then
I think that's misleading. It's a subset, but the only subset being we don't let floating point operators.
Yeah.
That's the only subset.
But you have to convince the compiler not to do that.
Yeah, that should be pretty easy. I mean, if you don't use floating point inside.
The compiler can decide that it's going to use the floating point unit just because it feels like it.
Fortunately, we're out of time, so we'll have to continue.
That's fine. Good.
Floating points. More floating
EVM
points.
versus...
What about Julia?
Sorry?
What about Julia?
Julia, I think, Christian, you're going to cover Julia a little bit in the flexibility, solidity talk later.
Not too much. I mean, Alex talked about it in quite big detail, so.
Yeah, well, it's a very active debate, EVM 1.5 versus eWASM. Hopefully we can, through the magic of transpilation, come to a united front and move forward with the evolution of the with evolving the EVM.
3.0.
Thank you.
What do we do with our...
Okay, hello. After the next presentation, we're going to... Nice music. After the next presentation, we're going to break for lunch. We'll reconvene back in here at 1 o'clock. Next up, we have Martin Swende, and he'll be talking about Aetherium Security.
Hello, my name is Martin Holst Svende, and I am the security lead for the Ethereum Foundation. Today I'm going to talk a bit about EVM forensics and managing attacks against the network and how we've been working on that. So I've been security lead for 1 year. I started just before Devcon3 in Shanghai last year, which started off with the Shanghai Attacks roughly 1 day after I started my new role. It kept on for a month. We've also seen during the last year we have done 3 hard forks. We've had 1 unintentional consensus split. There was a DOS attack against specifically the Geth client. There has been thousands of Ether stolen in more and less sophisticated attacks, both on-chain and off-chain. We have had the testnet totally brought to its knees and then resurrected again. And of course there's the standard IT incidents with leaked databases and someone taking over someone's phone number and their account and attacking our GitHub and stuff like that. So we should all be very clear about where we're at. This is crypto land and we're all in crypto land. And it's like Australia, where anything with a heartbeat will try to kill you. And if you make a mistake, you're probably dead. So, meanwhile, for attackers, they have never had it better. They no longer need to hack point of sales computers and trade carding details over shady forums. They can just hack a computer and or somehow get some cryptocurrency and immediately turn it into value. And it's like a Wild West in Australia right now. These are the Shanghai attacks. I'm not going to talk that much about them. The first Shanghai attack is that little blip down there. And then it just kept on going for a month. And it was a lot of different attacks, mostly targeted towards Geth. But when the dust is settled after incidents happen, then that's when you can actually do something about them and think about how can we be better prepared next time something similar happens. And how can we prevent it? So how can we improve the readiness and the resiliency? So for readiness, it's about detecting attacks and performing analysis quickly. So we started improving that with some monitoring, adding up some monitoring nodes that we run in the cloud and adding some graphs. Turns out there were some inherent issues which hadn't been noticed before with transaction propagation inefficiencies, which over the course of a few months in the beginning of, from January 3 to March, we managed to bring down the overall network traffic with about an order of magnitude just by removing invalid transaction propagation from the clients. On these monitoring nodes, we also added some interface so that we can extract very detailed information about what are the canonical blocks in the chain. And if we see a consensus split, we can get very detailed information about the receipts and differences in these and quickly point out which transaction caused this consensus issue. So here you see there's a geth master and geth develop and the parity node. And right in this image, they're differing on two fields marked in red there, and that's because parity RPC interface exposes a few different fields than geth. Now, as we go into analysis, I'm going to talk a few words about the EVM, because there might be a conception that any minor difference in the implementation of the EVM will automatically result in a consensus failure, and that's not quite true, because there are some things, some parts of the EVM which are ephemeral, such as the memory and the stack, and which do not necessarily trigger consensus issues. But they're very interesting because they can be used to trigger consensus errors. And in order to really measure EVMs side by side and detect implementation differences in EVMs, we need a kind of op-by-op view of the internal state. So we pushed kind of hard to get a common output format for EVMs, so that after each instruction made in an EVM, it would output a JSON blob with the internal state, as you can see on the left. And also a capability to use arbitrary pre-state and genesis configuration with the raw EVMs. So one problem that can arise is if we're hit by an attack which blows the node out of the water. How can we analyze that? Because our node just died, right? How can I analyze a transaction if the transaction crashes my node? Well, if we have a standalone EVM, what we can do is we can just fetch the pre-state about the sender and the receiver, just those two accounts. And we can execute that locally in our EVM and then analyze the trace to find, did we miss anything? Was there anything else we should have had here? And external references, and fetch those and start over. And if the node crashes, then we've successfully reproduced the API, the transaction. And for this, we only need a Web3 standard API without any debug specialities. Sorry. So I'm going to demonstrate quickly how we can do analysis of the jump test attack, which we were hit by on June 1. So I'm running this little reproducer here. I pipe in the hash used in the attack, the transaction, telling it I'm going to use my local EVM, not through Docker. And it basically sets the right fork rules for that particular block and executes it. And it has some intermediary traces here. We can take a look at those. So well, let's go directly instead for the final trace. I'm showing this in what I call the op viewer. or retro mix if you like. It's a remix like debug viewer for the JSON output format that I showed earlier. And this is a good start for analyzing what's happening in a transaction. So you can see this particular transaction, it does an Xcode copy. And the Xcode copy fills the memory with 5B. And it does it repeatedly. And as you can see, the memory is growing. And it keeps doing this for about 600 steps. I'm going to go a bit faster here. Until it has filled up the memory with 0.5 megabytes, all 5B, which happens to be jump test. Then it puts some more code in there. And this looks like actual EVM code, 6003565B. And all of you, I'm sure, recognize that that is the push one, jump test, and stop. So it just executed a create with that code. And as you can see, the size of the create is the full 0.5 megabytes. Okay, so now we know that the attacker is doing creates, and he keeps doing it repeatedly. One part of the memory changes between each invocation. It's a little counter down there, and I'll skip forward a bit. So it's all just create, and it ends on create number 105. It goes out of gas. So by this time, you can kind of have an idea. So it's doing creates lots of times with a large memory segment totally filled with jump tests. It changes 1 little byte each time, so obviously bypassing any caching mechanisms. So by reproducing it and viewing at the trace in this fashion, we can do a very quick analysis of what happened. And we can benchmark it. Right now it's running at 300 milliseconds. And if I compare that to, so this is the EVM, get EVM with the patch applied after this attack. I can try it against the EVM without the patch for the jump test analysis. And as you can see, it took 9 seconds. So this tooling makes it possible for us to do quick analysis and then to check, does this patch work? And I can share it with the coworkers, and they can try out various patches and see which one is the best. I can also run this in a web-like format and do all the same things, and investigate other on-chain events. For example, sorry, which one did I take? That was the same. The parity wallet attack. And there we have the parity wallet attack reproduced. And you can run it locally, or you can check an annotated trace of what happened there in the parity wallet attack. And for example, yeah, so here's the fated infamous delegate call and the null attack if you wanna analyze that more in depth. So the EVM lab, which I showed you a part of, makes it possible to do some EVM assembly Pythonically and investigate these kinds of issues and yeah, dissect attacks on a really low level. We had 2 hard forks also, and in preparation of those, we ramped up the testing, introducing parameterized tests or generalized tests, which Dmitry talked about yesterday in the breakout room. and also put it all into Hive. Hive is Peter Szilagyi's super cool framework for running nodes in a black box fashion, and just synthesize the environment, the genesis and the blocks and everything. And then you can compare the expected post state after a sequence of blocks. And this makes it possible to run, it runs about 24,000 test cases against Pytherium, Parity, Geth, and CPP. And it runs it 24/7, 365. It removes the dependency of the developers to perform tests as part of the test process. So now testing can be a totally separate process which doesn't really rely on the developers per se. The fallout, however, after the second hard fork is that we had a consensus issue, which was, definitely not what we wanted. Manually crafted tests are great, but there's no way to scale it due to the inherent complexity of the EVM. We can't just have enough people know that much about it to be able to scale it up. So we wanted more coverage for Byzantium and started looking into fuzzing. One way of doing that would be to generate test cases randomly, execute them on each EVM, and use this shared output format to compare the internal state after each operation, and just repeat it. And this can be done fairly quickly. You can do a couple of million tests per day if you use raw binaries, and you can use these 4 clients. The second track is based on libfuzzer, where we got in touch with Guido Rankin, who has done a lot of fuzzing and is a real expert on libfuzzer. So libfuzzer is the core of American Fuzzle Up. It's a fuzzer developed by Michal Zalewski. And it's a bit more sophisticated because it uses code paths and instrumented binaries to detect code paths for any given input, and then mutating those inputs to maximize the code coverage. And since everything is instrumented and compiled into one big binary, it is an order of magnitude faster to perform these tests. So it can do about 100 million tests per day. And there was a spectacular and kind of unexpected success in this. We've had 7 or 8 consensus issues found. Most of them before the hard fork. One of them slightly after the hard fork. It has been fixed and patched and released. And the clients today, I would say, are more thoroughly tested than they have ever been in the history of Ethereum. And we're still running fuzzers 24/7, and it's been millions of tests done on the testnet and billions of tests based on libfuzzer. Naturally, there can still be consensus issues or denial of service issues, and if that's really, really a concern of yours, then you should run multiple clients and try to detect mismatches. And you can use the debug method in Geth to find out if Geth has tagged one of Parity's canonical blocks as bad. And key takeaway here is that everyone here are targets for attacker. It's in bold because it's important. So be paranoid and be proactive and work on improving the security and your resilience and how you can handle attacks. That's about it for me. Thank you.